Linear Programming Notes, Advanced Algebra 2. What we're going to study in this video is a method creating a system of inequalities that will model a real-life situation, and then using the graph of those inequalities to look and maximize or optimize a situation. Let's just jump in and do some examples, and you'll get the hang of it. Okay, so there is a process for linear programming. The first thing is we will look at our real-life situation and we'll define our unknowns, our variables, and we're going to use x and y because we're going to be graphing on Desmos using x and y coordinates. Then you're going to write a system of inequalities based on the situation to represent the limitations on the situation. Sometimes these limitations are called constraints. We will write a profit equation because oftentimes the situation will want to maximize a profit, or just an equation of optimization. So the situation will call to optimize something about it. Then we're going to graph the systems of inequalities using Desmos.com rather than graphing by hand. Once we do that, we will find what's called the coordinates of the vertices of the feasible region. So the very outer edges of the region that fits all of those constraints or limitations that we put together. And then we're going to determine which combination of those variables, which of those vertices will answer the question, will maximize or optimize the situation. So let's look at situation number one. A calculator company produces a scientific calculator and a graphing calculator. Long-term projections indicate an expected demand of at least 100 scientific and 80 graphing calculators each day. Because of limitations on production capacity, no more than 200 scientific and 170 graphing calculators can be made daily. To satisfy a shipping contract, a total of at least 200 calculators must be shipped each day. So try not to get overwhelmed by these situations, and we will just break them down. Now here's the question, the problem we need to solve. If each scientific calculator sold results in a $2 loss, but each graphing calculator produces a $5 profit, how much of each type should be made daily to maximize net profits? So following our system or our process, we're going to define the variables. We need to know how many scientific and how many graphing calculators this company should produce each day. So let's let x equal the number of scientific calculators and y equal the number of graphing calculators. Now look back into the problem to find out those limitations. So it says that projections indicate a demand of at least 100 scientific calculators. So let's write a system of inequalities. So that would be x is greater than or equal to 100 and at least 80 graphing calculators. So y will be greater than or equal to 80. And then our production capacity limitations is that no more than 200 scientific and 170 graphing calculators can be made each day. So that means that together, the graphing and the scientific, so x plus y, needs to be, that x needs to be less than 200 because we can't go over that, and y needs to be less than or equal to 170. And then finally, for the shipping contract, it says a total, so we're going to add up x plus y, scientific and graphing, and it needs to be at least 200 calculators each day. All right, once you have your system of limitations, then what we're going to do is write our what we call our profit equation or our equation of optimization. So for each scientific calculator, the company will lose $2. So we'll multiply -2 times the number of scientific calculators, and then each graphing calculator will draw a profit of $5, so plus 5y. Now what we're going to do is graph these systems of inequalities on Desmos. So you just set up a Desmos account, hopefully you already have one set up, and then start graphing. Now take a minute to go ahead and enter the inequalities that I have, all the ones that we specified based on the situation. Then what I'm going to do right now is I'm going to turn on the shading for each one of them one at a time so that we can track our feasible region. So the region that satisfies all of these situations, these inequalities. So right now I'm looking at the pink region. Now I'm going to add y is greater than or equal to 80. So now I'm looking in this purplish, so the double shaded region. And now I have narrowed even further. So I'm looking at this strip here that has all three of those shadings. And now I'm down to this rectangular region here. And then finally, so what I'm going to do is mark the edges of this region that satisfies where I have all my shading. Now what these represent are different combinations of scientific and graphing calculators that could be produced that would somehow optimize. See how they're right on the edge of this feasible region? So minimize or maximize. So let's go back and let's capture each of those combinations, and then we'll plug each of those combinations into our profit equation. So our coordinates are 100, 170, 200, 170, 280, 120, 80, and 100 and 100. Different combinations of those two types of calculators to test. We will plug each one of those into our profit equation and see what we get. So if we plug 100 and 170 into our profit equation, the company would get a profit of $650. The second combination of 200 and 170 would give a profit of $450. The third combination would give a profit of nothing. And then the fourth combination gives a profit of $160. And the fifth combination gives a profit of $300. So you can see that the company's best bet is to produce 100 scientific and 170 graphing calculators per day to maximize the company's profits. All right, that's how linear programming goes. Now, in future assignments, I'm going to ask you to capture your Desmos graphs, and this is what I would like for you to do a screen capture where you get both the graph region with the shading and all of the points marked, and you can see how I did that earlier is I just clicked on the corners to get those ordered pairs to come up, and then also make sure that you capture these inequalities. So when we take a look at it, we can match the inequalities with the shading if necessary. All right, let's look at example 2. So a manufacturer makes wooden desks, and we'll just call the desk, number of desks X and tables Y. Each desk requires 2.5 hours to assemble, 3 hours for buffing, and 1 hour to crate. Each table requires 1 hour to assemble, 3 hours to buff, and 2 hours to crate. The firm can do only up to 20 hours of assembling, 30 hours of buffing, and 16 hours of crating per week. Profit is $3 per desk and $4 per table. So we want to maximize the profit by figuring out how many desks and how many tables per week this firm should manufacture. So let's set up our variables. X is the number of desks and Y is the number of tables. Now this is interesting. Look back in the problem and notice it gives information on assembling, buffing, and crating. So that's how we're going to organize our inequalities. So let's first write an inequality or a limitation for assembling. So for assembling, it takes 2.5 hours per desk, so 2.5 x plus 1 hour for tables, so 1 y. And then altogether, the company just has 20 hours that it can afford for assembling, so it's less than or equal to 20. For buffing, it's 3 hours for desk and tables, and the firm only has 30 hours, up to 30 hours that it can devote to buffing. And then finally, crating. So 1 hour to crate a desk, 2 hours to crate a table. And then the company can only spend up to 16 hours per week for crating. So sometimes You have to just look through and figure out how to organize your situations. So we're told that the profit is $3 per desk and $4 per table. So that will be our profit equation is 3x plus 4y. And now go to Desmos and let's graph this on Desmos. All right, so I already have these inequalities set up here. So take a moment and enter them on your Desmos. And then I'm going to turn on the shading, just one limitation at a time. And what we want to keep our eyes on is the shaded area. Now we want to look at the double shaded area. So now we see that this is what we call our feasible region. And now let's go and mark our corners of the area that has shading on all three. Sometimes you'll get a situation like this where your amount will not end up on an integer. And so in that case, we just need to think common sense. What values would satisfy the equations? Even though our tendency would be to round up to 7, if we did that, we would be out of the feasible region. We would be out of all of the triple shaded area. So we're going to round down, and this combination will be 6 and 3. So let's consider 0 and 8, 4, 6, 6 and 3, and 8 and 0. So we'll plug each of these into our profit equation one at a time. And we can see with the first combination, we would get a profit of $32, with the second, 36, with the third, 30, and with the fourth, 24. So to maximize profits, this firm needs to produce 4 desks and 6 tables per week. And this would be what your captured Desmos graph would look like. All right, let's look at example 3. Suppose that in order to raise money for homecoming, your class needs, oh, sorry, that's word a little, it should be your class needs to sell some items. The council decides that a sale fundraiser would be the best option and orders cases of Hershey bars and cases of jarred popcorn. However, the student council also decides that your class can order no more than 400 candy bars and jars of popcorn and spend no more than $500. How can your class maximize its profits? So look at the table with a little bit more information. Hershey bars come with 30 candy bars in a case. Popcorn comes with 10 jars in a case. We are going to pay $10 per case for Hershey bar and sell them for $1 each. You're going to pay $20 per case for popcorn and you sell for $5 per jar. So what we're trying to find out is how many cases of Hershey bars and how many cases of popcorn you would need to sell to maximize the money coming in. So our system of limitations. Notice that we can only sell, or rather order, no more than 400 candy bars and popcorn altogether. So there's 30 candy bars in a case, so 30x is our number of candy bars plus 10y is our number of popcorn jars, should be less than or equal to 400. For a second limitation, it's 10x. Because our cases of Hershey bars cost $10 plus 20y, because our cases of popcorn cost 20, needs to be less than or equal to 500. So that's our money limitation. And then just some common sense limitations that each of these numbers of cases should be greater than or equal to 0. So now here's our profit equation. We're going to make $20 per case for Hershey bars and $30 per case of popcorn. And then we want to graph our inequalities. So we'll do that on Desmos. And I'm going to turn on my shading and then we can see our feasible region here. So we've got 3 different combinations to check. 0, 25, 6, 22, and 13, 0. So for the first combination, it's 750. For the second, it's 780. And for the third, it's 260. So to maximize, we need to sell 6 cases of candy bars, and 22 cases of popcorn.